Greetings everyone. So in this video we are going to discuss about the new topic Grignard's reagent and amines. We have understood a very basic concept about various reagents which have been used uh, for doing hydrogenation, dehydrohalogenation, hydration, dehydration. But the reagent which we are going to discuss today belongs to a specific class of organic compounds known as organometallic compounds. What is an organometallic compound? Organometallic compound is such an organic compound which is having a metal atom attached to it. If you just take examples of these organometallic compound in our nature, that's chlorophyll in the plants, which is used for catching sunlight. And then we have uh, hemoglobin, which is used for catching oxygen in the human blood. So it contains iron, chlorophyll, while contains magnesium. Both even are having the same structure. Both have porphyrin and both have the tetrapyrrole ring, the porphyrin ring. But the only difference they have is the central atom, which is iron in hemoglobin and magnesium in chlorophyll. Likewise, we have certain organometallic compounds we can synthesize artificially as well. For example, we have dimethyl zinc. Dimethyl zinc. What is that? That's an organometallic compound used as insecticide. We have methyl cobalamin. It is a derivative of the vitamin B12, derivative of vitamin B12, cyanocobalamin, which is methylcobalamin. And then um, the very famous, we have very famous tetraethyl lead, tetraethyl lead, and that again is an anti-knocking agent. We have also understood that when we react, sodium lead with alkyl halides, we basically get tetraethyl lead and tetramethyl lead as a with a byproduct, which is the byproduct. So this is pretty helpful. This is pretty helpful for us to understand. And then we have another type of organometallic compound, which is the Grignard's reagent. What is Grignard's reagent? If you just talk about Grignard's reagent, it was discovered by a chemist, Victor Grignard, in the early 1900s, for which he also received a Nobel Prize in 1912 because of the importance of this compound. This compound is extremely reactive. It is very reactive class of organometallic compounds, and that has the capability to form almost any organic compound. We can form carboxylic groups from this. We can form esters from this. We can form ketones from this. We can form um, we can form alcohols from this and what not. So a lot of things can be made with the help of reacting Grignard's reagent with a particular set of organic compounds. So let's just understand um, some of the key aspects. Basically, what a Grignard's reagent is, it is a magnesium atom. It is a magnesium atom attached with an alkyl chain and a halogen group. This is just basic structure of a Grignard's reagent. Now, if we just look into this structure, we will find one thing, that alkyl group over here is having the sp3 hybridized orbital, while magnesium is having the atomic orbitals. While same goes with the halogen, which is also having atomic orbitals. In this, we do not see such of uh, geometry. The only geometry we can see is in the alkyl chain because it is sp3 hybridized. But we just look into its reactivity. On the basis of the reactivity, we see that magnesium is an electropositive atom. It is electropositive, electropositive, and because of being electropositive, it is willing to give its electron away to the more electronegative chains, which include carbon and halogen. So, due to being electropositive, it makes the alkyl chain partially electronegative and the halide chain, the halogen atom, partially electronegative. So, because of this, the alkyl carbon which is present in the Grignard's reagent acts as a nucleophile. the nucleophile carbon of Grignard's reagent, which will react with the electrophile carbon of a functional group. It can react with any electrophile carbon. So again, these are certain reactivity characteristics of this compound. Now if you just look into how is it prepared, it's prepared through a very simple mechanism. An important point to remember is that whenever we are going to react alkyl halide, it is to take an alkyl halide and react it with magnesium atom, react it with magnesium in the presence of an anhydrous, in the presence of an anhydrous ether. What is an anhydrous ether? Ether which is without any sort of protons. It is anhydrous or dry ether. Why do we take a dry ether or anhydrous ether? The reason behind it is that the Grignard's reagent is a very reactive species, reactive compound, and that reactive compound can actually result into an explosion or any sort of other chemical reactivity which can be harmful. And that is why we always use whenever we are going to perform any reaction involving Grignard's reagent or the preparation involving Grignard's reagent, we always check anhydrous dry ether. And alongside that, what we actually do is when we take ether and then we provide it a bit of heat, we will get this. And what do we name it? We name this as alkyl magnesium halide. It is named as alkyl magnesium halide. And let's just look into the reactions it performs. Reactions are pretty simple. Basically, the first reaction which we are going to have is the reaction with the reaction with aldehydes and ketones. Whenever the Grignard's reagent is going to react with aldehyde or ketone, it's going to produce, whenever it reacts with aldehyde or ketone, it's going to produce alcohol. Now, the point to be considered here is that if it is going to produce, let's say, if it is going to react with a formaldehyde, then it will produce a primary alcohol. If it is going to react with ethanol or the acetaldehyde, then it's going to form secondary alcohol. If it is going to react with propanol or the first member of propanol or dimethyl ketone, we will get a tertiary alcohol. And all the ketones onwards will have a tertiary alcohol formed. So how does the reaction actually happens is the reaction happens when the Grignard's reagent is reacted with the ketone or aldehyde in the presence of anhydrous ether, and it is completed in two steps. The reaction mechanism is completed in two steps. Let's just understand those two steps. Number one step is number one step is attack of the nucleophile. Attack of the nucleophilic carbon on the electrophilic carbonyl carbon. So what actually happens is, let's just understand this, that what actually happens is, let's say this is the Grignard's reagent. What actually happens is this partially negatively charged alkyl group of the Grignard's reagent attaches with the electrophilic carbon, also known as alpha carbon of the carbonyl group, due to which it forms this complex. This is basically an intermediate complex which has a structure like this: carbon, CH3 over here, CH3 over here, and CH3 over here, CH3 over here, and what else was there? There was this OMGBr. Uh, and one more thing, it was an essential point that I really did not mention. Whenever we're going to take the halide in the Grignard reagent, the halide in the Grignard reagent is most of the time bromine. The reason behind it is that Grignard's reagent, the possibility of preparing a Grignard's reagent depends on two factors. It depends on two factors. What are those two factors? Those two factors are: number one, size of the alkyl group. Sorry, not the size of alkyl group, but the size of the halogen atom. Size of the halogen atom. Size of halogen and nature of alkyl group. So, if you just understand the first point, size of halogen. According to the size of halogen, we basically need to understand whenever we are having a bigger size, it's more difficult for the whenever there's a bigger size, the atom forms a more stable bond, due to which it's much difficult for the bond to be broken, due to which the ease of forming a Grignard reagent with a larger halogen atom makes the reactivity like this. Makes the reactivity like this: chlorine greater than chlorine, greater than bromine, greater than iodine. But if you just take it in consideration with the nature of the alkyl process, that when alkyl group attaches with halogen, then we consider the reactivity as this: iodide greater than bromide, greater than chloride, greater than chlorine, chloride greater than fluoride. This is a reactivity when it comes in consideration with the alkyl group. So whenever we are going to take in consideration the reactivity of the Grignard's reagent, the type of halogen atom which is supposed to be used in the Grignard's reagent, we are neither going to take, we are neither going to, you know, totally depend on this factor, nor we are going to totally depend on the other one factor, which is the size of halogen. We would rather depend on an intermediate which has got an intermediate reactivity in both point of views, such that if you just see size of halogen atom, bromine is the atom which is having an intermediate size. Likewise, the intermediate bond which is going to be easily broken is alkyl bromide. So whenever we are going to take a halogen atom, we do not take fluorine, or we do not take iodine. We most of the time take bromine as the halogen atom in the Grignard's reagent, and this is an important point to be considered. Anyways, let's just move on to the point where we left off. All right, so over here, this is the oxygen with which the magnesium and bromide attached, and alongside that, over here we are having the over here we are having another CH3. We are having another CH. So what actually happens is, when this molecule reacts with a water molecule, I take a water molecule. Now, it's important to understand that after it is put in a dry ether, uh, some amount of water is added, um, in the presence of an acid, due to which and acid hydrolysis happens, and that acid hydrolysis causes the cleavage of this bond. Cleavage of this bond. Here comes a proton. Proton comes and attaches with the proton attaches with the oxygen, and on the other hand, due to which it forms a separate compound, due to which this entirely forms a separate compound. Let me just make it more clear. Here comes a proton, and proton comes and binds with it, due to which oxygen gives it its electron here, due to which it forms this entire part separates and forms hydroxy magnesium bromide on one hand side, and the OH part on the other hand side. OH part on the other hand side attaches OH part on the other hand side attaches with the terminal carbon the OH group attaches with over this side. At this point the OH group comes and that forms a tertiary alcohol. So this is how the mechanism goes on. The first step of the mechanism is the attack of the nucleophilic carbon on the electrophilic carbonyl compound, and number two step is acid hydrolysis of this intermediate complex. This intermediate complex. This is the fact to be considered. Now let's just move on to a few more things that we need to understand. There is a very simple chart that we need to understand in order to get through this concept. If you're going to have an ester, and I'm going to react ester with a Grignard's reagent, then at that point I'm going to produce a carbonyl compound, aldehyde or ketone. When a carbonyl compound is going to be attacked by a Grignard's reagent, it will produce an alcohol. And when an alcohol will be attacked by a Grignard's reagent, it will produce alkane. So this is an important mechanism that we need to understand. Alright. So now let's just move on to the next part, which is a few other reactions which it performs. Number one, another reaction is with carbon dioxide. Whenever the Grignard's reagent is going to react with carbon dioxide, it's going to produce carboxylic acid. How? Let's see. Again, the same mechanism happens. The nucleophilic carbon of Grignard's reagent attacks on the electrophilic carbon of carbon dioxide, due to which it forms a complex, and then complex is hydrolyzed in the presence of an acid, due to which it forms carboxylic acid, acetic acid. This is the reaction. After that, we have a few more reactions left. We have done reactions with aldehydes and ketones, and yes, there are a few more reactions, which number one includes the reaction with amine. Whenever there's going to be a reaction, whenever there is going to be a reaction with amine group, with an amine, then at that point it's going to produce an alkane. When Grignard's reagent reacts with an amine, then it's going to produce alkanes with this compound, magnesium amine bromide, amino magnesium bromide, amino magnesium bromide, amino magnesium bromide. And another important thing to understand over here is that when it reacts with cyanogen chloride, when it reacts with cyanogen chloride, then it's going to produce a nitrile, a nitrile. It's going to produce a nitrile. So now let's just move on to the next part, which is amine. Amines are basically the groups which include this NH2. Now in this case, the hydrogen can also be replaced by some other alkyl groups as well. This is the actual structure. This is the actual structure of an amine. Amine is basically having sp3 hybridized orbital. 4 sp3 hybridized orbital. 3 of them are bond with alkyl groups. There can be alkyl groups or hydrogens in case of the 3 bonding sp3 hybridized orbital, and one of the sp3 hybridized orbital has the lone pairs. And because of the effect of repulsion between the lone pair being the highest, it causes to create a tetrahedral structure, but that tetrahedral structure has an angle reduced to 107.5 degree, which is a pyramidal structure, like a pyramidal tetrahedral. And an important point to understand is whenever we are going to have a primary amine and secondary amine are not optical, are not optically active, optically inactive. But when you are going to have a tertiary amine, which is having all three all three alkyl groups attached, then that is optically active. These are some examples of the namings. These are some common names. This is ethylamine, that's secondary hexylamine. This is isohexylamine, which is a primary amine. And then we have dimethylamine, a secondary amine. And let's just move on to another part. These are some crucial names of crucial amines. Pyridine is an amine, is a tertiary. Pyridine is a tertiary amine, and we have trimethylamine. And on the other side, we have aniline, aniline, which is basically amine group attached to a benzene ring. This is amine group attached to a benzene ring, aniline. And when it's going to react with methyl group, then it's going to make a compound which is paramethyl aniline, and that paramethyl aniline, oops, the paramethyl aniline is also known as, this paramethyl aniline is also known as, let me just draw the structure, toluidine. And that's something important to remember, toluidine. Alright, so let's just move on to its structure. If you just look at its structure is pretty basic. Tertiary amine, which is having 3 alkyl groups, is optically active, and it is basically having nitrogen, which is an electronegative atom, and because of being more electronegative, it basically makes the alkyl groups which are attached to it electropositive. Alkyl groups which are attached to it are electropositive, and due to this reason, the alkyl groups which are attached to it become electropositive, and alkyl groups attached to it become electropositive, and they are able to invite a nucleophile to attack on them. So this is a general reactivity. If you just talk about its physical properties, methylamine is a gaseous amine. Methylamine is in gaseous form, and if you just talk about all other amines from diethylamine to the upper classes, we are going to have them in the liquid forms. There is quaternary amine. When the quaternary dialkylamine dialkyl ammonium, which is basically an ammonium salt. It is a salt which exists in a crystalline form. It is having a quaternary structure, and that is in a solid form, crystalline salt form. Also, it is colorless, but it has a fishy odor. It has a fishy odor. That fishy odor increases with the um, it increases with the number of alkyl group. For example, methylamine has a low fishy odor, but trimethylamine has a very fishy odor, which is also found in the fishes because of the trimethylamine present in their body. Um, Found in the body of fishes and the body of the dead organic matter as well. And on the other side, if you talk about its melting and boiling point, because it is nitrogen is electronegative atom, and the group which attaches with nitrogen becomes electropositive, due to which nitrogen is able to create hydrogen bonds, and these hydrogen bonds make the melting and boiling point of amine group as higher. Also, because it forms hydrogen bonds, it has a higher solubility as well. It has a higher solubility. But again, there's something that needs to be considered. Solubility decreases with the increase in the number of carbon atoms in a hydrocarbon chain, as well as the solubility decreases with the increase in the number of hydrocarbon chains. For example, if you're having methylamine is highly soluble in water. But if we talk about trimethylamine, it is barely soluble in water. It has a very limited solubility in water, due to which it is also used in the osmoregulation mechanism in the fishes. What actually happens is fishes intake a lot of trimethylamine in their body, due to which they are able to increase the solute concentration, due to which the water directly enters into their body through passive transport without the expenditure of any energy, which makes them able to sustain themselves in a dying environment, in a watery environment where they actually need a lot of water to survive. And that's something pretty beneficial for fishes like sharks and other such fishes. So anyways, this is about it. And if you just talk about melting and boiling point, it has the same trend, such that when we increase the number of hydrocarbon chains, the melting and boiling point decreases. All right, now let's just move on to another part, which is the basicity. What is the basicity of amine group? Amine group, if you just compare amine group, if you just let's say compare methylamine with ammonia, methylamine versus ammonia, we will find one thing, that ammonia ammonia is having greater value of pkb, while the value of pkb is greater, but for methylamine the value of pkb is less. What does this mean? We know that whenever the value of pkb for a compound is higher, it means it is less basic, and the value of the pkb is less, it means the compound is more basic. And due to this reason, we can say that the basicity trend of basicity is in this manner. Basicity is like this: methylamine is greater than ammonia. Methylamine greater than ammonia. So this is one of the reasons we can get mathematically. But if you just look into it, the actual reason of it, we will find that the alkyl amines are having greater basicity than ammonia group, because the carbon which is attached to nitrogen in any sort of alkyl amine is having sp3 hybridized orbitals, and we know that sp3 hybridized orbital has 25% s characters and 75% p characters, and because of 25% s character, it is less close to nucleus, It is far away from nucleus, less close to nucleus, and due to this there is less nuclear attraction. There is less nuclear attraction of the carbon atom towards its electron, due to which it is um more happy to give its electron. It would say that I don't have much power, nuclear attraction over my own electron, so you can take it away. So it would ask that please take my electrons away, because nitrogen is already electronegative, and if it is not having, if the electrons are not having any sort of a nuclear attraction from the parent atom, the electronegative nitrogen would be more than happy to take them away. So the electron cloud density is saturated towards nitrogen, due to which nitrogen becomes more negative. Nitrogen's negativity increases, due to which the basicity of nitrogen ultimately increases in an alkyl amine, which becomes greater than ammonia. And on the other side, if you just take ammonia, ammonia has s orbital of hydrogen. S orbital is present nearest to the nucleus, due to which it has greater nuclear attraction, and makes ultimately the nitrogen less negative and thus less basic as compared to methylamine. So that's how it explains. But if you just compare, um, on the basis of this part, the strength of the basicity of alkyl amines. We just compare this part, that how alkyl amines are basic. So we have three types of alkyl amines. We have primary alkyl amine, we have secondary alkyl amine, and we have tertiary alkyl amine. So if you just look back into this principle, on the basis of the principle which we discussed right now, the trend of basicity would be like this. It is supposed to be like this, right? But the problem is tertiary amine has something we call as a steric hindrance, also known as a steric effect. And that steric hindrance of effect stops the proton or any sort of positive agent to come and attach with the negative nitrogen in order to perform a neutralization reaction, and that ultimately reduces the reactivity of nitrogen, as reduces the reactivity of nitrogen as a base, and thus its basicity, when it is dissolved in any sort of solution or when it is reacted with any acid, ultimately decreases. And due to this reason, we do not keep this here. We do not keep this here. We rather keep this. We rather keep this here at the end, because of the steric effect it produces. So the trend in actual is this: secondary amine greater than primary amine, greater than tertiary amine. Now let's just move on to another important point, which is the preparations. Preparations are pretty easy. If we just take the first example, we have the alkylation process. Alkylation process happens when I'm going to take an alkyl halide in an alcoholic ammonia solution, and we react alcoholic ammonia with alkyl halide in a sealed tube at 100 centigrade. 100 centigrade. At that point, we will get alkylamine, and we will get a byproduct, which is ammonium halide. Now, if you just look into alkylamine, that the alkylamine which is going to be produced initially would be primary amine, and that primary amine, when it is going to react further with another alkyl halide, it will produce a secondary amine in this reaction. And then when secondary amine will react with hydrogen iodide, any sort of hydrogen halide, sorry, when it is going to react with another hydrogen iodide, it's going to produce tertiary amine. And when tertiary amine will further react with another um, alkyl halide, then it will produce ammonium salt. This is basically known as an ammonium salt. And ammonium salt, we also call this as a quaternary diammonium salt. A quaternary diethyl quaternary ethyl quaternary ethyl ammonium salt. Let me just write it as well. Quaternary ethyl ammonium salt. All right. So now let's just move on to another reaction. Whenever we are going to, react, whenever we're going to prepare prepare amine, we can also prepare it by reduction of certain nitrogen-containing groups. For example, when we take nitrile, we can reduce nitrile by performing its catalytic hydrogenation, such that we take either aluminum oxide or hydrogen, or we take aluminum oxide or nitrogen. Sorry, we either take aluminum oxide or nickel or platinum at 300 centigrade in the presence of hydrogen. Then at that point, we can actually make a primary amine. If you're going to take, let's say, uh, benzyl benzyl cyanide, then at that point, that benzyl cyanide can actually form benzyl amine. And when it reacts with, let's say, methyl cyanide, it produces primary amine. So in that way, it's pretty helpful. Catalytic reduction, that was a catalytic reduction. And then we have another type of reduction where we can use chemicals to perform the reactions. For example, we take tin in the presence of HCl, and we react a nitrobenzene. In the presence of tin and HCl, we actually get the aniline, and that aniline um, is produced. After that, we have some other reactions as well. When we take, let's say, nitrobenzene, nitro nitroaniline reacted with iron in the presence of H2SO4, we will get um, aniline amine. On the other hand side, when we are going to react any sort of let's say, if I'm going to take, let's say, a carbonyl compound, let's say I take aldehyde, and I cause its reduction with the help of a strong reducing agent like lithium aluminum hydride, then that is going to produce a tertiary amine or secondary amine or primary amine, depending on the type of carbonyl compound I had. And an important point to remember over here is that whenever the carbonyl compounds react with are reduced, it's not the entire compound which is reduced, it's only the carbonyl group which is reduced to methylene group. And while the entire molecule remains intact in this reaction, only the carbonyl group is reduced to methyl group in this reaction, which ultimately leads to the formation of tertiary alcohol or any other sort of tertiary amine or any other sort of amine. And then there is reaction of amide. When we are going to, there are basically two reactions with amide, such that the first reaction which we are going to have is whenever amide reacts with lithium aluminum hydride. When we are going to react amide with lithium aluminum hydride, then it's going to actually produce the tertiary amine. Sorry, it's not tertiary amine, actually it's a primary amine. When lithium aluminum hydride reacts with amide group, it's going to produce primary amine. And there's another reaction which is known as Hoffman's degradation reaction. Hoffman's degradation reaction. And that Hoffman's degradation reaction is in such a manner that if you are, let's say, going to take Hoffman's degradation reaction is in such a manner Hoffman's degradation reaction is in such a manner that we are going to take bromine. We are going to take a halogen. in the presence of potassium hydroxide, and we reacted with amide, then we are actually going to get methyl amine, or a primary amine essentially, with a carbon dioxide molecule. So in this reaction, one carbon dioxide molecule is released, which is basically the carbonyl group, which is released, carbonyl group which is degraded from this compound, which is known as the Hoffman's degradation reaction. Now let's just look into a few more reactions which are done with amine. Amine, whenever reacts with alkyl halide, it's going to produce its secondary form, and then when with secondary form, it can form a tertiary form, and with tertiary form, it can essentially form its uh, quaternary form. So this is the reaction we understood previously. Let's just look into this reaction. When amine reacts with an aldehyde group, when amines react with an aldehyde group, aldehyde or ketone, they are going to produce, when amines react with aldehydes or ketones. Yes, this is a reaction actually. So let's say if I take an amine group, this is an amine group, right? And I'm going to react this amine group with an aldehyde. Let's say I'm taking a ketone, okay? So these are the two chains of ketone, two alkyl chains, and this is the ketone group, and this is amine group. When I'm going to react both of them, what I'm actually going to get is, I'm going to get, in the presence of HCl, right? So what actually happens is, what I'm really going to get is this part hydrogen, and this part oxygen. It will eliminate. It will be condensed into H2O, and rest of the part which will be left will be this R N C R R, and over here there will be a double bond formed between nitrogen and carbon. This is known as Schiff's base, also known as imine group. Imine group. This is a very important reaction to remember. After that, we have got a few more things to understand over here, such that um, whenever we are going to react amine group with a nitro, when we are going to react amine groups with oops, when we are going to react an amine group with an acid chloride or acid anhydride, at that point we are going to produce amides. We are going to produce amides, and that would be done in the presence of a base. That should be done in the presence of a not a base essentially. It should be done in the presence of an acid. And let's just move on to another part, which is a reaction of amine group with nitrous acid. When nitrous acid reacts with amine below 10 centigrade, in the presence of HCl, and at that point it basically forms diazonium ion, that basically forms this ion. This ion. This is a very unstable ion known as diazonium ion. Diazonium ion. And that diazonium ion is a very unstable ion. Above 10 centigrade, it decomposes into alcohol. It decomposes into alcohol and nitrogen gas. In order to increase its stability, we can react an aniline with nitrous acid to form a benzyl diazonium ion. But again, that benzyl diazonium ion also above 10 centigrade can be decomposed into a phenol and a nitrogen gas. So if you just look into its practicality, it has no practical applications because we cannot practically use it for any reaction. We cannot use it for any sort of reaction that's going to be beneficial. So these are certain important things which are important to be discussed. And also, when it's going to react with a hydroxyl group, when amines react with let's say when amines are going to react when amines are going to react with let's say amines are going to react with carboxyl groups, then at that point they are going to produce when they are going to react with carboxyl groups, they are going to produce amides. Reaction with carboxyl groups produce amides, and their reactions with alcohols produce amine. So these are two things that were needed to be mentioned. Alright, so that's all about today's video. Hopefully you enjoyed it, and hopefully we will meet in another video.